So we're going to start and kind of build our way up. Again, remember, we're in Chapter 2. Chapter 2, we're talking about just first-order differential equations, not any higher orders than that. So our differential equations will only have first derivatives in them. They're ordinary differential equations, so they have only one independent variable. And we're not looking at systems yet, so we only have one dependent variable. So we're looking at y's and x's, or x's and t's, or y's and t's, just one dependent, one independent variable. So there's not a sledgehammer approach to differential equations where one tool will work for all of them. In fact, all of our tools will be very specific to a type of differential equation that we are able to solve. So it has to meet some criteria before we can apply that particular method. And so as we go through Chapter 2, we're going to start with the first group, which is the easiest of all, what are known as separable differential equations. Depending on who you had for calculus or where you took calculus, you may have actually seen these in like a Cal 2 applications of integration. But if not, it's basically at the level of Cal 2. It's not too bad. Being able to integrate is all you really need if you come across a differential equation that happens to be separable. In the next section after that, we look at linear differential equations, and I'll give you a technique that will solve all first-order linear differential equations. And the next one after that, we'll look at exact equations. It's another criteria that an ODE has to meet in order to be exact. So once we find out if it's exact, then we apply a technique. Then there'll be some, the rest of them are either modifying something that's not exact into one that is exact, or doing substitutions, plugging in a replacement formula for one of our variables, and will turn out to turn it into one of those that we do know how to solve. And then that's kind of where we wrap up in this section of doing separable, linear, exact, and then with a whole bunch of substitutions. I will mention at the end of Chapter 2, the one kind of sledgehammer approach that we do have that doesn't get us an exact solution, doesn't get an analytical or closed form solution, but can get us a numerical approximation of the solution. That is, maybe I don't know what the actual formula is, but to whatever degree of accuracy you want, I can find what the curve shape would look like. I can find all the points that are on that curve, even if I don't know the formula for the curve. I say all with quotes around it. I can't actually find all the points, but I can find as many as you want me to, as accurate as you want me to, if I have enough computing power to approximate it. That's numerical analysis. We'll look at a couple of numerical techniques in this chapter, and then more later on in the semester. Okay, and that'll be what we try to do in section 2, or chapter 2. Okay, so let's now start with separable. That's my introduction. So separable equations are equations like this right here. That makes it called separable. So what's the key property of that formula that I've got written there? Notice my differential equation up here. dy dx is equal to f of xy. That is a differential equation. It's ordinary. It's first order. And it's in normal form. Those are all terms we introduced in Chapter 1. Ordinary because there's only one independent variable. First order because there's only one derivative and it's to the first order, first derivative. And it's normal because it's solved for the highest order derivative, in this case dy dx. Okay? So that's a general differential equation. Those are the ones we're trying to solve in this chapter. If it has the property that the right-hand side, that f of xy, is a product of a function of only x's times a product of a function of only y's, it's called separable. And that means I can separate these, put all the y's in one function, all the x's in another, and say it's multiplied together. Then I'll be able to essentially move the y's to one side of an equation and the x's to the other through multiplication and division. Okay? So as long as you can write it as a function of x times a function of y, we will call it separable. So this part A on the example, is that a separable equation?
Yes.
Absolutely. It's x times y squared. So that x is your g of x. That there is your p of y. By the way, I'm using p instead of h. It seems natural that I would say h there, but there's a reason, because of notation used in the proof later on of this method. I will introduce an h in a different way. All right, so again, notice a function of your independent variable times a function of your dependent variable. In part B, is that separable?
Yes. The other variable isn't there.
The other variable isn't there. So if the other variable isn't there, I can think of it as a times 1. Right? A constant function is a function of any variable. Right? If it's not a function of a variable, then it can be a function of any variable. I could write, the function f of y is 1. That's true. That is a function that depends on y. It just means for every y value, the output is 1. Okay? Or in this case, my two variables that I'm looking for are a and t. So I've got a function here of my dependent variable, I said it right, dependent variable, and a function here of my independent variable, okay? So this was separable, and this one is too separable. Does it make sense why, those of you that said no?
Wouldn't all autonomous functions be separable?
Every autonomous function would be separable under my reasoning, right? Because you could always write that other part as a function of t, and autonomous means there is no t. Right? So yes, we can always, just like you can always write something as times 1, you can always write something as times a function of another variable, assuming that the function is 1. So that's separable. Now what about the last one? You can't separate sine of x times y. That's not sine of x times sine of y. By the way, there's no identity that lets you do that. Okay? So you can't separate that into two functions. While it is a product inside, I couldn't write it as a function of x times a function of y. Does not equal that, okay? Not possible. Okay. So you'll want to be able to identify those things. What you should have as just an initial question on every differential equation you have to solve from this point forward is, if it's separable, it's easy, you can do it straight away. So always check if it's separable first. Be able to eyeball a differential equation and just see. If it's separable, I have a solution technique, okay? And I'm about to show you what it is. It's to separate it, essentially. If it's not separable, then we move on to more exotic, more useful, more techniques that handle different types of differential equations. Okay, so essentially what we're going to do is break every rule of calculus. I shouldn't say every rule, but a very important rule, okay? Treat dy dx as a fraction. Remember, that should make you cringe. You never treat dy dx as a fraction. Every time you do treat dy dx as a fraction, it, what did I say? A kitten dies, a dog dies, somebody, an angel loses their wings. Yeah. Okay. I'm fine with cats also. That's just fine with me. So maybe something a little more close to home for you. An Xbox One crashes.
Oh, that's what
Red ring of death. Okay. I'm going to take the dx and move it over here. I'm going to take the p of y and move it over there. That's what I'm going to do. It's illegal, but trust me, I will prove that it works later on, that by breaking the law here, it's just an easy way and a convenient way to treat the notation, but I will prove to you that the antiderivative of 1 over p of y dy equals to the antiderivative of g of x dx is a solution equation to the original differential equation. That's what I will prove to you. Because then we integrate both sides, and what we're basically doing is integral of p of y dy equals the integral of g of x dx. Okay? And I'll prove that this is equivalent, or this equation here in its implicit form satisfies the original differential equation. That's the proof that I will give you so that we're allowed the license to get away with treating it as a fraction. Okay? But you also got to remember, don't forget the constant of integration. I didn't write it explicitly, and I'm going to kind of put this off to the side so that you see it. What this ends up being is, in fact, I'm going to do one little small adjustment of notation that you'll see again in the proof. I'm going to call this h of y. So what I really have is h of y dy equals g of x dx. Just whatever you end up with on the left-hand side times dy, let's call that h, which happens to be 1 over what I call p. And so then I integrate both sides of that. What I'll get is the antiderivative of h, little h, is equal to the antiderivative of little g, but plus a constant of integration. Now you may wonder why I don't just put a constant of integration on both sides. Well, if there's just a constant on both sides, and they're not necessarily the same, that's the same as just one constant. I could move that one constant that's on the left over to the right, and that creates a new arbitrary constant. So I only have to include one constant. And then the last step is, if possible, you solve for y, or solve for the dependent variable. Okay, so what allows this method to work is, as long as you can multiply or divide to get all the y's on one side, and multiply or divide to get all the x's on the other, then you integrate both sides, and the resulting equation is a solution equation. Okay, so let's say I've got dy dx here is equal to x minus 5 over y squared. Is that separable?
Yes. Just split the money, multiply dx, multiply the y on two sides.
Yeah. I could write it like this to prove it's separable. X minus 5 times 1 minus y squared.
1 over y.
Yeah, sorry. But again, the easiest way to think of separable is, can I separate it? Meaning, can I do like what Dylan was saying, is move that y squared over the other side, right? And move the dx over here. So I'm going to take this y squared, I'm going to multiply it to this side, and I'm going to take the dx over here, and even though I'm wincing, I'm going to move that dx over there. Another cat. Sorry. So that's y squared dy equals x minus 5 dx. Integrate, integrate.
Are we substituting the h of y this time or no?
No, that's just for notation's sake. Just up here, I wanted to think of whatever's over here as h, whatever over here is g. I'm not going to label them as g and h as I'm actually solving. I'm just doing the action of moving the y's, moving the x's, integrating, I'll be done. Okay, those were just placeholders for, in general problems, whatever you get over there I would call h, whatever you get over here I call g. But you don't have to do that in practice. So that's 1/3 y cubed equals 1/2 x squared minus 5x plus c. Yes, sir?
Is it just a coincidence that we had the y squared in the fraction form when we switched it with dx, or can we just have like a whole number and put it there?
What do you mean?
When we're swapping the dx
Uh-huh.
from the other side, I mean, is it just a dependent variable, or does it have to be in fraction form when we do it?
No, it could be anything. Like I could, if I had like dy dx is equal to x sine of y.
Mm-hmm.
That's not a fraction, right?
Right.
So I could end up with 1 over sine of y dy equals x dx.
Okay.
Right? Just divide it across.
Right. Okay.
Yeah. So it can be multiplied, it can be divided. It can't be added. You can't subtract across. Because if you subtract across and then when you multiply the dx, you'll end up with dx's showing up in terms on both sides. It doesn't work.
My only question is, why don't we put a c on the left side as well?
Okay, so if I did do that, and well, I'll come off to the side here in another thought bubble. What about 1/3 y cubed plus some c, right? Equals 1/2 x squared minus 5x. Now, it can't be the same c, because you're not required that whenever you integrated the left-hand side, you know, that arbitrary constant means that's true for any constant whatsoever. If I put the same c on the other side, I'm saying it is only true for that same constant I used on the left side. So I'd have to give it a different constant. So maybe I'd call this c1 and call this one c2. right? Now, this is an arbitrary number. It's true for any C1, right? This is true for any C2. If I subtract this C1 over to the other side and have 1/3 y cubed equals 1/2 x squared minus 5x, I would have a C2 minus C1, right? Now, since C1 is arbitrary, C2 is arbitrary, then C2 minus C1 is arbitrary. I'm just going to call that some other arbitrary constant.
Okay.
So it takes the place of both of them together. We will actually do a little bit of hand waving and mathemagic with constants throughout the semester, keeping in mind as we go that if it's an arbitrary constant, because it's arbitrary, if I have another arbitrary constant, I can just slam them together. Okay? And make it one new arbitrary constant. One other trick that will annoy you to no end, or at least it did me whenever I was first taking this, is that sometimes we'll come along the way and we'll say, that's an arbitrary constant c, but instead of putting c, I'm going to put the log of c. Because if c is an arbitrary constant, then so is the log of c. You're like, why would you put log of c? That just makes it more complicated. But it actually simplifies it later on whenever I start solving for y. So we do weird little magic tricks with constants along the way. But there are some rules, and I'll make sure to point them out as we go. In the end, I now multiply, but if I can solve it, I need to solve it. In this case, I can solve it as a function, because taking and solving for y, I can take the cube root of both sides and end up with a closed form solution. It explicitly solve for y, right? This would be y is equal to the cube root of 3/2 x squared minus 15x plus
C over
3c, which, if c is an arbitrary constant, then so is 3c. So he just kind of absorbs that 3. I mean, technically what I should be doing along the way is exactly what I did over here on the right-hand side. I could call this new c, I would let c equal, if I was formally writing this out, I'd say let c equal c1 or c2 minus c1, and then I plug that c in. And then over here, I might call this c prime, where c prime is actually 3 of the c that I was talking about over here. I don't always technically do that. Maybe it's sloppy on my part, less formal and rigorous, but the point is, if c1 and c2 are arbitrary constants, then they're differences. If c is an arbitrary constant, then any scalar multiple of it is. So I'm just going to call it c and get away with it. Don't you love that?
We do happen to put 3c because we're not.
I will not count it wrong. I don't know if the homework does. I don't think it does.
Okay.
I mean, if you've done Maple before and you've done integration in Maple, which you probably should have done, I think you've seen it in calculus, whenever you do a general or an indefinite integral, it puts a plus little c underscore 1 in there like that, right? It adds a constant, and it adds a different constant for each integral that you put into a problem. What it doesn't do is combine those all together. It's doing more like what you should do formally. But it should not count off if you put 3c or c. I think it should know the difference. I can't guarantee that, though.
Wait, is that a solution that we just came up with?
Yep, you want to check it? I claim that this, y equals cube root of 3/2 x squared minus 15x plus c, solves the original differential equation that we started with.
Can we plug that back in and find a...
Well, we don't have an initial value problem yet. If I told you, off to the side, if I had said y of 0 is equal to, 4, then you could find c. Right? What I'm saying is that this equation here solves the original differential equation, no matter what c is.
Okay.
But then when you're given an initial value, then that's where you find a specific c. Cube root of, I think that's right, 64 in that case. But if you had put 3c in there, then c would be something different. It would be 3 times some number that equals 64, right? And if you've got the C1 and the C2 in there, where you end up with a problem because you have two different constants and only one condition. So if in a single step you introduce multiple constants, you should always combine them together into one constant because they're not really distinct constants. That's one of the rules I'll talk about in more detail later on. If in two different steps you introduce a constant in one step of integration, and then later on in the problem you've done something in our derivation of a solution, and we do another integration and introduce a second constant that's arbitrary, you generally aren't able to combine those unless they're just added together. What ends up happening is you got like a C1 times a function plus a new C1 got introduced. You can't anyway combine those, and you'll see that as we go. I'm kind of foreshadowing something you'll see explicitly when we get there.
So during application, even if you solve your differential equations that you designed for them, they still have to have at least some results for you to be able to.
Right, you need to know which particular curve. You got to know where you're starting to have a particular integral curve, right? We think of the direction fields, right? We knew that solutions exist all over the plane. Not until you pick a specific point do you know which curve goes through that point, which of all that infinite family.
Right.
On a first order differential equation, you always have one parameter families of solutions. So there's one unknown like the C. In a higher order, there'll be 2 or 3, and so you've got to have additional conditions to know explicitly which solution we're talking about. All right, let's try this one. Is it separable?
Yes.
Easy multiplication, division actually will move that to the other side, and what I end up with is dy and dx on opposite sides. On the right-hand side, I'll have a 1 over x plus 3, and on the left-hand side, 1 over y minus 1, right? What I'm doing is I'm multiplying both sides of this by 1 over y minus 1 to move that to the other side. Integrate, integrate. What's the integral of 1 over y minus 1?
Natural log 1 minus 1.
Absolute value y minus 1. On the right-hand side, same thing, right? Natural log of x plus 3, all plus, how about log of c?
Sure.
Hey, why not? You'll see why in just a second, why that makes good sense.
Since we're going about all this, I'm going to start calling that out loud.
Would you just say it in your head, don't say it out loud. I have to start bringing things to throw
We're
at you.
making stuff up.
Okay, well, if you do that, you have to be consistent, and now you have to spell out every function that we ever introduce. SIN and COS and SEC, TANs. EXPONENTIAL.
So if we say it's fine.
Ulm?
Ulm?
Just say log. It's so easy to say log.
But it's the natural log.
Yes, and that's the only log you need. Those common log morons do not need to be using the common log.
Why did you learn a common log then?
Exactly. Why?
I don't
Because
want
there's
to call
idiots
that.
out there that use it and shouldn't be using it. You need to convert them. The natural log is the only log you will ever need. You can quote me on that, okay? Did you know there's one of these too? There's an LG that they use in computer science
Okay.
a lot, and even bioinformatics too. That's the log base 2.
That makes sense.
It's an important one because binary, but in at least for example in bioinformatics, what you're studying is large data sets from these high throughput data machines that they've got in biology for like sequencing genomes or finding out which genes are turned on and turned off, or what their expression levels are. And so it's always important to know what's called fold change, is how many times the size or the expression level doubled. So like, you know, if your expression level was at 2 and then later on it was at 16, it doubled 3 times, right? 2 to 4, 4 to 8, 8 to 16. So your fold change would be 3. So you're using log base 2 to figure that number out.
Is there a name, a nickname for that? Is it like the,
No, it's still another thing that morons use.
Genomic
You still
law?
only need the natural log.
the genomic laws or something?
Look, I don't know. I don't actually know if there is a name for that. I'll let you go Google it and find
Can we
out.
still solve for y?
Solve for y. How would we solve for y now?
E to the,
E both sides? Exponentiate is the word. Yes.
exponentiate.
Yes. Exponentiate both sides, which I do by doing that. Okay, e to the both sides. Right? And so e to the natural log of y minus 1
1 minus 1.
is absolute value of y minus 1. By the way, I'll be able to clean up the absolute value in just a second with the c. It'll be nice. On the right-hand side, okay, here's where this comes into play. I'm going to come off to the side so you can see this. You have e to the natural log of x plus 3 plus, nope, plus up here, natural log of c. Yeah, right on this thing today.
Does,
Or just log of c.
doesn't it get rid of the natural log though?
Well, if you're adding, you're just multiplying together.
Exactly. This is e to the natural log of x plus 3 times e to the natural log of c, right? You're using the multiplying two exponentials with the same base. You add their exponents. And now, what's e to the natural log of c?
C.
It just cancels out and leaves you with c. So you have c, and the first one cancels out also and leaves you,
Absolute value of x plus 3.
right,
What? For time?
it's times, right? Because of this times right there. That's why I put a natural log of c in there, because if I didn't, I would just have e to the c, right? If I hadn't put log of c, I'd have e to the c. And this is then when I'd do my hand waving and say, well, if c is an arbitrary constant, then e to the c, a constant to a constant, right? A fixed constant to an arbitrary constant is still just an arbitrary constant. So I just put c there anyway. So by doing log of c earlier, at least I get the joy of crossing out an e in a natural log. Okay. Now what about these absolute values? Well, the absolute values are essentially sign corrections that tell you whether or not it's going to be positive or negative on the right-hand side or positive or negative on the left-hand side. The sign is going to be determined by which function we talk about as the solution. So this c right here, for lack of a better way to explain it, absorbs the absolute value. Aren't these constants awesome? So basically this is saying y minus 1 is equal to c times x plus 3. I don't have to worry about the absolute value.
Because the sign doesn't depending on the sign of C.
Do what now?
Because the sign of the absolute value is like
It's just going to be a positive or negative in the problem, right? So if the solution I'm looking at has y values where it's below 0 or where y minus 1 is negative, then I would just put a negative on the left-hand side, right? Because the absolute value of anything
it's positive.
is either a if a is positive or negative a if a is negative, right? And so you've got just a sign, either a 1 or a negative 1, that I could just move and put in with that constant, depending on where I am. Okay? So if I add 1 to both sides, I've got y is equal to c times x plus 3 plus 1. Okay? Now that is a solution to the differential equation. I asked you to solve the initial value problem. So what do I got to do next?
Plug in your values.
Right. So I need to make a little space here. I'm going to continue on over here. So use y of negative 1 equals 0. That would give me 0 equals c times negative 1 plus 3 plus 1. So negative 1 equals 2c, which means c is negative 1/2. So y is equal to,
1/2, negative 1/2 x plus 3 this one times.
which would be, I mean, you can leave it that form, that would be correct. I could also simplify this. Negative 3/2 plus 1 is just negative 1/2, so this is y is equal to negative 1/2 x minus 1/2, I believe. Either one of those works. So it's just a line, slope negative 1/2, passing through the y-intercept of negative 1/2. So the solution to this differential equation up here is just, or actually the initial value problem up there is just that line.
So this is the actual math magic that we hear about in our tutoring session. What kind of magic is this?
Mathematics.
That's a cosine, that's not magic.
Yeah. I mean, there is sound rationale behind each one of these steps. Again, combining arbitrary constant into being a new arbitrary constant is basically substitution. I'm just happening to be reusing the letter C instead of like a C1, a C2, and a C prime. I just want to show you the most common technique. Whenever you see, basically, here's the way to plan ahead with the log of C business, why I introduced log of C instead of just C, is if on the left-hand side you have 1 over a function of y, and you know you're going to get the natural log show up with y inside, and your very first step for solving is going to be to exponentiate both sides, then use log of C instead of C. That's really the only time we'll ever do that. Okay? So far I've only done 3 little tricks. I make it sound like we're doing all kinds of crazy illegal things with our constants, but we're not. One, if they're just constants together, added together, or even multiplied together, or even scalar multiples of them, I can just replace that with a new constant. Okay? Exponential of a natural log. The other trick was to plan ahead and put this log of C in here instead of just C. But the technique for separable equations is pretty straightforward. Get the y's on one side, x's on the other, integrate both sides, solve for y. However, sometimes that last step is not even possible, the solve for y step. So I wanted to show you at least one of those where it's still easy to solve, but it's still easy to solve the differential equation, but you can't get an explicit solution out of it. Right? You should be able to see this one pretty quick. This is separable. Everybody see that it's separable?
Yeah.
Since all the y's are on bottom and all the x's are on top, I could think of it as the top times 1 over the bottom. So this gives me cosine of y plus e to the y dy equals 6x to the 5th minus 2x plus 1 dx. Integral of cosine of y. Oh, integrate. Boom, boom. Sine of y plus e to the y. That's the integral of cosine plus e to the y. Right-hand side is x to the 6th minus x squared plus x plus c. Last step would be solve for y if you can. You can't. And so you're done. And when I say if you can, I don't mean if you can. I mean if it is possible to be done. Okay? No, can't do it. That's too complicated. I have to add something to both sides. No. You can't do it in this case because the y is inside an exponential and inside a sine. There's no way to separate the y from both of those. So then you surrender.
Does the purpose of solving for y just make it easier to solve your initial value problem?
Well, no, you can actually solve the initial value problems in implicit form. That's relatively easy. It's just a better form to work with in terms of when you have the solution. If you have it in functional form, they're easy to graph because all you got to do to graph those is plug in a bunch of x's and see where the y's goes.
Right.
Graphing implicit functions, deriving implicit functions, just working with implicit functions in general is much more complicated mathematically. So we're kind of laying the groundwork for what would we do when we got a solution. Now, if you're thinking homework, you're going to type it into WebAssign and click check my answer. But I'm thinking more generally as a mathematician or engineer, what are you going to do with your solutions? You want to graph them, you want to use them, you want to use them to predict. So having it solve for y is the better form for using those tools. So that's why you solve it when you can. You can leave it in implicit form only if Dr. Franklin can't solve for y. You don't have to actually write my name on there. You can just say you. But you get the point, right? All right, proof of method. Why am I allowed to kill cats in this process? So show that dy dx is equal to, I don't want to write, I'm just going to do a proof. So g of x times p of y. So let's start with the original problem, which was g of x times p of y. We want to show that that leads to the integral of h of y dy equals the integral of g of x dx. I have not proven that because I only used an abusive notation to do that, right? That's like saying you can't abuse notation by just crossing out the ends. That doesn't work. What I've done so far is just as wrong as that is. So let's prove why it actually works.
Is it almost as wrong as you could just give every American $4.3
Yes, $1 million, sure. For the record, if you really care about poverty, you do away with it because giving all the money back actually gives back less than just not having the lottery in the first place. Because the only people that are really playing are the people who soapbox don't have the money to play. I mean, if real investors thought it was a good investment, I mean, if you actually thought it was a good idea, then the people who had $292 million to buy all of the tickets would just buy all of the tickets, win, and come out ahead. But you don't ever come out ahead. As Dr. Hahn says, you are more likely to die on the way to buy your lottery ticket than to win the lottery. You're more likely to be struck by lightning twice inside your home than to win the lottery. The Powerball, that is.
I'm sure Dr. Hahn would love to give like a guest lecture on that.
Well, he was actually interviewed. I don't know if you guys saw this. If you were on our, if you follow us on Facebook, you saw that he was interviewed by a reporter. Actually, they called me up, and I directed them him because I knew he had strong feelings. He was stronger, and his carry a little more weight as the stat professor actually talks about this in his classes. But he was interviewed by the Lubbock Avalanche Journal. He had a whole article about right before the Powerball was won. So you need to go find us on Facebook, and it's one of the links that we have on.
Is it the win math page or is
Yeah, the School of Math and Science.
Somebody won.
definitely.
There were 3 winners. I have only heard about who one of them was. But 3 tickets were purchased. That's what last I had heard. Okay, let's focus here. Come on. I actually have to let us out early today.
No.
I'm trying to get myself in a good mood by doing all this fun stuff today because I've got to make a presentation to the Board of Trustees.
Oh, that's
That is today. dy dx is equal to g of x p of y. So we'll start there. And for notation again, let's let h of y be 1 over p of y. So I'm just introducing the variable h now that will show up in my conclusion of this proof. Okay? Now, the first thing that I can do is with the assumption that p of y is non-zero, I can say this implies that 1 over p of y dy dx is equal to g of x. No abusive notation there, as long as p of y is non-zero. Okay, now, let me define capital H of y as the antiderivative of the h of y function. Oh, hold on. Let me actually then write this as what I want it to be, which is h of y dy dx is equal to g of x. Right? I'm just using my new function name that I just declared up here. Okay. So I also want to introduce the capital named functions, capital H and capital G, because that's what's commonly used in calculus whenever we talk about the antiderivative function. So I'm going to call h of y whatever the antiderivative of h of y is with respect to y. And I'm going to call capital G of x the integral of g of x with respect to x. So they're the antiderivative of those functions. Okay, so this is the same thing as saying that h prime of y is equal to h of y. Right? That's what it means to be the antiderivative. H is the function that when you take its derivative gives me the integrand h of y. And g prime of x is equal to g of x. So I'm assembling all the little pieces that will go together to form the proof of this. As Dr. Alms used to say whenever he taught me these things, he would say, a good proof is kind of like taking a whole bunch of pieces of lumber and nails and throwing it up in the air, and then all of a sudden it comes down and it's a doghouse. So that's a good proof works that way. You get all the pieces just right, throw it up in the air, and it lands, it's the doghouse. So we're going to throw all these pieces in the air, and it's all going to fit together nicely, okay? So, okay, so come back to here. I've got h of y dy dx is equal to g of x. Okay? So this here is just g prime of x, right? I claim this here is h prime of y dy dx. Right? Again, I just put what from these two lines right here. Replace little g with g prime, little h with h prime. Now here's the hand wave, not the hand wave. Here's it lands as a proof.
The prestige.
Just switching my notation on the right-hand side, g prime of x is just d dx of g of x, right? It's the derivative of the g with respect to x. The advantage, by the way, in my opinion, of the Leibniz notation, the d notation, is that it tells you what variable you're taking the derivative with respect to, right? This h prime here, because the only variable in there is y, that's derivative with respect to y, right? All right, now here's the trick. That right there is the derivative with respect to x of capital H of y. Nope. I now say that this whole thing here is the chain rule. I've basically reversed the chain rule. Right? If I told you, well, I'll come off to the side here in a bubble. If I gave you an h of y that depends on x, and I said take the derivative of that with respect to x, what does the chain rule say that you do?
H prime of y.
Right, yeah. You take the derivative of the outside with respect to the y, right? H prime of y of x times the derivative of what's inside, which is y prime or dy dx. Notice I get h prime of y dy dx. It's the same thing as just d dx of h of y. When we assume that y is a function of x, which it is, right? Because y is the dependent variable. So the left-hand side is simply d dx of h of y. Now I can integrate both sides with respect to x. Okay? This is d dx, this is d dx. So I claim then that if I integrate d dx of h of y dx equals the integral of d dx g of x dx, the integral of the derivative is the function itself, plus an arbitrary constant. The other hand waving that I did in the earlier proof was I just took the integral of both sides, but on one side I was taking the integral with respect to dy and the other one with dx. I'm claiming now that on both sides I've got essentially a function of x, right, inside here, because y is a function of x, and then the derivative of that, they're equal. If the derivatives of two functions are equal, then their integral of the derivatives are equal, which means the two functions themselves are equal, with a possible difference of a constant. But by definition now, from right here and here, I have that the integral of h of y dy is equal to the integral of g of x dx. And I can include the c as the constant that comes out of those integrations. Proof.
Does the box be included?
Yes, the box is your ultimate goal in any math class. That should be what you strive for, that you've proven the result.
Excellent.
Okay? I mean, essentially what I've done here is I've used my notation correctly to get to the same conclusion, that the integral of h with respect to y is equal to the integral of g with respect to x. This equation comes directly from the original differential equation and thus satisfies that. Okay? Follows. All right, last thing I wanted to do, just because I want you to see it, and the rest of these separable equations are actually pretty easy to do. You'll just have some to practice. How much? I got 15 minutes? Actually, I tell you what, I'm not going to do this one right now. I'm going to go ahead and break even earlier than I originally anticipated. I need to make sure that I'm ready and all set up for my presentation with the board. So, you guys have what you need to be able to do the homework. I'm actually going to record a video of the suspended cables. All these are is two new models, like I did in 1.3, where I introduced some new models to you, some equations in practice, so you know what the shape of certain solutions are to differential equations, what they mean. In this case, if you've ever been driving down the road and you look up and you see the cables hanging between the power lines, and you've wondered, I wonder what the function is of that curve as it hangs there. And you think, well, it kind of looks like a parabola. It must be a parabola. Well, you're wrong. It's not. And we can use differential equations to prove why a suspended cable hanging on its own is not a parabola. It does not form a parabolic shape. It forms what's called a catenary. I'll prove to you that it's a catenary in section 5.3, but for now, I would derive what the differential equation is, and then make the claim that if you happen to be visiting somewhere that has a suspension bridge, and you see that same shape, where the cable is holding up a bridge instead of just holding up itself, that curve actually does form a parabola, whereas the cable by itself does not.
Okay.
And the differential equation shows you why one is a parabola when it's suspending a bridge of uniform density, whereas one that's only holding up itself is not a parabola. I'll prove that for you in a little video that I'll get posted later today. I know you are dying to know why.
I really am.
I will show you. See you guys on Tuesday. The homework is assigned and ready to go. Make sure you get it done by Tuesday.
Jay, what up?